Hi everyone, thanks for checking out this video. So this is going to be a lesson about the Monte Carlo simulation method. So I'm going to try to explain the concept of that to you guys and show you like a basic kind of simple implementation in Python. And this lesson will also be kind of like a PSA about why I think you should avoid casinos. So you're going to see why in a second, but I guess I should really say like if you should avoid casinos unless you're just going for fun. Like if you're just going for fun, for the experience, to have a good time or whatever, I guess that's okay. But if you're trying to actually make money, then you should definitely avoid casinos because, well, you're going to see why in a second. Okay, but before we get into all that and before we get into the Monte Carlo simulation method, I'm just going to tell you guys about this casino game of Roulette. So, just in case you're not familiar with this game, I'm just going to kind of tell you like the basic rules, and we're going to talk about, and then I'm going to ask you guys a question related to it, and think about how to answer the question. So in roulette, we have this like roulette wheel that's it's spun around, and then a ball is dropped in, and then when the wheel stops spinning, wherever the ball lands, you can like bet on where it's gonna land, and wherever it lands will determine like whether you win or lose the bet. So these are all the like slots where it can land, and they're numbered and color coded. And there are a bunch of different ways to like bet on this, like different sort of bets you can make. But just to keep it simple for this lesson, we're just going to talk about the color betting. So you can either bet on it to land on a black slot or a red slot, and if you get it right, the bet pays out 1-to-1 odds, which means if you bet $5, if you win, you get your $5 back plus $5 more, and if you lose, you lose your $5. So it pays out on 1-to-1 odds, but you might notice actually that whether you bet on red or black, you're going to have slightly less than 50% chance of winning, because you can see there's two slots here that are neither red nor black. There's two green slots here. So when you're betting on like a red or a black slot, it pays out as if it was 50-50 odds, but really it's slightly less than 50% chance of winning. And this is why I was saying that if you guys are trying to make money, you should just avoid casinos, because basically all the casino games are sort of you're not getting fair odds. You're getting odds that are slightly biased in the direction of you losing money over time. Because I mean that is how the casino makes money. Is they don't if they gave everyone fair odds, they would just not be able to make money. So all of their games they kind of have like slightly less than fair odds. So again, it can still be fun, I guess. But if you're trying to make money, yeah, you shouldn't be going to casinos. But okay, so enough of that rant. So I'll just before we get into the simulation stuff, I'm just gonna ask you guys a question, and we're gonna think about how to solve it. Okay. So this is the question. So let's say that you start off with $100 and you go into a casino with $100, and you say that you're just gonna go up to the roulette table and you're just gonna bet on red every time and keep betting $5. You just are just going to keep betting $5 again and again and again. Um, and we know, because we just said you're getting slightly less than fair odds. We know from that eventually, in the long run, you'll eventually run out of money and go to having $0 left. So we know that, but the question is, what's the expected number of games you'll play before you run out of all your money? So just to rephrase, you're betting on red $5 every time, making these $5 bets. If you win, you get a net profit of $5, and if you lose your $5. And we want to know what's the expected number of games you'll play before you run out of money if you're just doing this continuously. Okay, so maybe just think about that for a second and think about how you would approach solving this question. Okay, so if you're like me, you probably didn't right now just figure out the answer, because it seems like a problem that can be solved analytically. Like you could potentially just write out some equations on some paper and try to work your way to the answer analytically, and that's kind of like the mathematician's approach to kind of just ponder over this problem and try to like write down some equations and figure out the answer. But yeah, like all that hard work is for mathematicians. We're computer programmers, so we like to just just get the right answer the easiest way possible. Like as long as we're getting to the right answer, we want to solve it in like the fastest and easiest way possible, right? So this is where the Monte Carlo simulation method comes in. So a Monte Carlo simulation it's basically a simulation that involves randomness, where you can learn something by repeatedly sampling this simulation. And this is going to make more sense when we actually write it. But so what I'm getting at here is, instead of trying to answer this roulette question by like writing down equations and stuff, an easier way to answer it, I think, is to actually just write a computer simulation of this game we're playing and just run it a bunch of times and sample our own simulation and then just look at the distribution of the results. So again, this is going to make more sense once we start running it. Just to give some like history too. This is the guy who invented it, Stanislaw Ulam. Yeah, famous mathematician. He actually invented it while he was working on nuclear weapons research. So kind of a like morally complex history. But yeah, so he was this mathematician who invented this method. But yeah, okay. So let's get into the programming. I hope this makes sense so far. So just to reiterate, the whole idea is that instead of solving this probability question by writing down equations or something, we're just going to solve it by writing a simulation of kind of the random process in question, and then sampling our own simulation to get a distribution of the results. That's kind of the idea behind a Monte Carlo simulation. But okay, so hopefully this will make more sense once I start actually like writing the code and explaining it to you guys. Okay. So yeah, so like we said, we're walking in with $100, so we're just going to have one variable keeping track of how much money we have. So let's call it my money. Set that to be $100 or whatever. And then we're interested in keeping track of the number of games that we play before we run out of money, because we know that since we have slightly less than fair odds, if we keep playing continuously, we'll eventually run out of all of our money. And we want to just keep track of how many games are being played until this happens. So we'll have a game count variable to keep track of the number of games. So then the way the simulation is going to go is while my money is greater than 0, we're just going to keep simulating this game, okay? And so the way we're going to actually sort of simulate the random probability here is we're going to use the random library, and we're going to use the randint function. So this basically just gives you a random integer in a range that you set. So we're going to set it to be in the range 1 to 38, and that's including the 38. So it's inclusive of both of these, this whole range here. So this will give us a random, and maybe I'll show it to you guys in the terminal too. Yeah, so basically just when we call this function, it just gives us random integers in this range. So the way we're going to do the probabilities is by calling these random integers. We're going to check and see if this is less than or equal to 18. I'll explain why in a second. So the reason for that is that it's kind of like we said. Yeah, there's 38. 38 of these slots, And 18 of them, which is slightly less than half, are red, and then 18 are black, and then 2 of them are green. So remember, this is where the slightly unfair odds comes in. Is that they actually don't, even though they're paying out 1-to-1 odds, you actually have slightly less than 50% chance of winning, because your probability of winning if you bet on red is 18 over 38, which is like slightly less than slightly less than half. It's um like 47%, I think, or something. But yeah. So anyway, we're basically checking to see because there are 18 red slots out of 38 total slots. We're basically saying if this random int is less than or equal to 18, we're going to count it as a win. So if we win, then we're going to say my money is going up by 5, right? And by the way, you guys could also write this like this too. The syntax. This is incrementing it by 5, but I'm just running it like the simplest syntax possible, just so if anyone doesn't know this this syntax, I'm writing it like this so that you can just follow it easier. But yeah, this is another option to write it too. Okay, and then else. So if that if statement isn't true, that means you lose, and if you lose, then my money goes down by 5 because you're losing $5 if you lose. And then so after we play the game, we also want to record that we have that we've played an additional game. So we're going to say game count equals game count plus 1. So that's just keeping track of how many games are played. And then so at the end, we want to just print simulation over, and then we'll print money left, which we already know is going to be 0, but we want to just see it to confirm. And then print number of games. Okay, so let's just try out this and just make sure it's working. So just to go over this again, it's just while we have a positive amount of money left, we're going to keep playing this game. And this random.random is simulating the probability of winning if you bet on red, which is going to be slightly less than 50% probability. And if you win, you get $5 profit, and if you lose the $5 that you bet. And then we're just counting the number of games that we played. Okay, so let's try this out. Okay, so it worked. So it says we have 0 money left like we expected, and the number of games for that run of the simulation was 386. But you can see that if you run it a couple times, you get a different number of games. So this is kind of the point of the Monte Carlo simulation, is that we have some kind of like system involving randomness that we want to simulate, and we can learn something by repeatedly simulating it and repeatedly taking draws from the simulation to be able to look at a distribution of results. So that's kind of the whole point of the Monte Carlo simulation method. But okay, so let's actually get this distribution of results, because I mean, if we just keep running it, I mean, you can see how different the results are each time. If we just keep running it like this, we're not really gonna be able to learn anything. So let's actually get like a distribution of results for the next step. Okay, so we're gonna put for each game count. Every time we run the simulation, we want to record that in some new array called game counts, plural. This will be an array that we can append to the results each time. And then let's just say for simulation count in range, make it 10,000 for now. we're going to basically run the simulation 10,000 times. And then, yeah. And then at the end of each simulation that we're running, 10,000 times, we're going to append the results to this game counts array where we're just recording all the results each time. Okay. And yeah, also, of course, just make sure that these variables are being reset for every iteration of the for loop. Otherwise, we'll get problems if they're not reset each time. Okay. And then, so this will give us a distribution of results from our random simulation. And then, so let's print out the mean of the results. And let's print out the standard deviation. Okay. Oh, and we better just comment these out for now because otherwise they're going to be printing out every single time. And then, so let's also plot the distribution of results too. So we can say plt.hist. So we want a histogram of the game counts distribution. And then for bins, you guys can make the bins whatever you want. I'm just going to set them a certain way to help us kind of visualize and like sort of get a nice visualization. But the bins is just kind of just how many bins are going to be used for the histogram. And I'm going to say, set the bins to be the int. We need to cast this to an int in case it's odd or decimal. So we're going to take the maximum of this this results array and divide by 4, and then just take the int of that in case it's a decimal or something. Okay, and then plt.show. And again, I hope I didn't confuse anyone with this line here. I mean, the number of bins, you guys can just make whatever. I'm just setting it like this so that we can kind of visualize it nicely. But you guys can make the number of bins, like, whatever. Oh, actually, it should be, plural. Yeah, hopefully this will work okay. Let's give it a try. Okay, so here's the results. So this is the distribution of all of the outcomes of the number of games played until you lose all your money. So as you can see, it kind of has a peak, an early peak, and then a wide right tail kind of. And then we print out our mean. Our mean is 376 point some decimals. And then we also have our standard deviation. So the mean here is like the expected outcome. This is what would be the expected number of games that you would play until losing all your money. We can see there's kind of a lot of variance too. You know what I mean? Because I mean there are some games, some of the simulations they played for like more than 1,000 games before losing all their money, and some of them even see. The real outliers here, like one of these was like more than 4,000 games before losing all the money. But anyway, this is kind of the point of the Monte Carlo simulation method. So just to like reiterate what I've been saying, it's useful when you have some kind of system that maybe could be analyzed like in a deterministic way or like mathematically. Maybe you could analyze it mathematically, but it's just easier to just write a simulation and take random draws from the simulation and analyze that distribution of results. That could be easier than like writing down equations and stuff. And yes, this is useful for understanding like systems involving randomness, as well as also it's used a lot in like optimization problems. Like one future video I might make is on another method called Markov chain Monte Carlo, which is basically like an optimization technique that uses a Monte Carlo simulation to try to optimize a function. So that's a possible like future video I might make. But yeah, so I guess I'm just saying that this has a lot of like potential applications that go beyond just like simulating casino games or whatever. But yeah, so hope that made sense to you guys. If anyone has any questions, just let me know in a comment. And yeah, thanks for watching, and see you next time.